Right, so in this video, what we're going to do is take a deeper dive into the concept of conservative versus non-conservative forces. So just to review a couple of things about them. So what we know is in the absence of non-conservative forces doing work, total energy is conserved, total mechanical energy is conserved, right? So the work done by non-conservative forces is equal to the change in total energy. Therefore, if the work done by non-conservative forces is equal to 0, therefore, we know that the initial energy of the system is going to equal the final energy of the system in some sort of time sequence. We've also talked about the fact that when conservative forces do work, it's related to the negative change in the potential energy associated with that conservative force. And hopefully you will remember that we can derive that because the work done by conservative force is the integral of that force vector, so that conservative force very specifically, dot with ds, right? And so we can then link these two equations and derive for ourselves, given a conservative force, what the equation for the associated potential energy is. The dot product in this derivation is what brings us from the vector quantity to the scalar quantity of the potential energy. And these potential energies are functions of position, meaning, and this is the big thing, that because the potential energies are functions of position and not how I get from one place to another, the criteria for conservative forces then is a conservative force is one whose work is path independent. Okay? Right? That is our criteria. And up to now, we've kind of taken that as an article of faith, that there are things that where the work done is not path dependent and work where it is path dependent. What we're going to do is go into a deeper dive with the calculus of that here. Now, the one example that, or probably the chief example that you have so far is the force of gravity, right? So if I have an object here at the ground and I move it from here to here, or if I move it like this, or if I move it like this and like that, whatever I do, the work done by gravity is going to be the same over those three paths. Well, gravity is sort of a trivial example. Why is it trivial? Well, this equation for the work done by a force is what we'd use when the force is non-constant, right? When it's a function of something else. When the force is not a function, we're just using magnitude of the force, magnitude of the displacement, cosine of the angle between the force and the displacement, or we're using, because that's really coming from, remember, the dot product, F dot delta S. And that could also be written as Fx times delta x plus Fy times delta y. Now, in this perspective, remember that when you're doing anything with dot product, you have to write your force and your displacement vector as ijk vectors, right? Because that's the operation of the dot product is dependent upon those structures, right? And so if we're talking about the force of gravity, we know that the force of gravity is negative mg j hat, right? Mg is its magnitude, which is constant as long as little g is constant, which we know it is on Earth on average, so no big deal there. And the negative j hat tells us direction, right? We've identified positive j hat is 1 unit upwards, negative j hat is 1 unit downwards, positive I hat 1 unit to the right, negative I hat 1 unit to the left. Those are definitionally true things. So if I look at that then, the Fy here is just mgy, and you'll notice then that any sort of horizontal displacement then is functionally not going to matter when we talk about the gravity force, because there's no horizontal component of this force, right? And all that's left mattering is the vertical displacement. Very specifically, the vertical displacement, not the vertical distance traveled. So even if I overshoot it and come back, it doesn't matter. All it cares about is the beginning and the end state. And that is because the relationship between the direction of the force of gravity and the magnitude of the force of gravity is invariant. It doesn't change. And therefore, I don't really have to worry about that. sure, gravity might do negative work on the way up, positive work on the way down, but negative work, this path would just be a lesser amount of negative work done by gravity. Why negative, by the way? Because the negative sign there and my displacement is upwards, right? And when I go downwards, the negative sign and the negative displacement is positive, right? So those two things kind of cancel out in the wash, and all we care about is the starting and the end point. But we're not really going to ever, in this idea, we don't really encounter forces that are constants, because it's fairly boring and fairly trivial. Now, on the other hand, let's just talk about friction for a second. So if I am, talking about this path and I'm moving along this path, at any given instant, if that is my ds vector, friction is always going to act opposite the instantaneous displacement, right? So the direction of the frictional force here is constant, not constant, excuse me, is constantly changing, and it's always aligning itself exactly opposite the local ds variable, which is why when we're talking about the work done by friction, the path matters, because the frictional force is actually a function of the direction of the displacement rather than being a function of position, right? So the changes in position affect the direction of frictional force rather than the actual instantaneous position of the object. When an object is at a given position, you can't tell what the direction of the frictional force is. But if I know it's going to move like this way along that path, now I know that that's the direction of the frictional force. That nature of the frictional force as being reactive to a displacement rather than a position is a reason why it's going to be path dependent and therefore not conservative, right? That the length of that path is going to be very much dependent on what the size of the work done by friction is, which is why when we talk about the work done by friction, we can actually kind of just collapse that, because really what we're doing here, if I'm going to be truly formal about it, right, is we know that if I'm thinking about, well, magnitude of the force of friction, magnitude of the distance, times cosine of theta, just to kind of like make this pretty obvious here, this is going to collapse to -1, right? Because my frictional force is always opposite the displacement of what it's in contact with, right? So I'm going to end up with a negative. The force of friction, as long as it's constant, we can use this equation. If it's not constant, once again, we do have to use the calculus version of this. But then you may be saying, well, this also says displacement. Right, but really, if I have a curved path here, what I'm doing is I'm adding up all those little ds's, right, in a vector sense, and that's why I end up with an arc length, which is why we can just replace that with d, the distance traveled. For those of you who are in BC calculus, you know how punishing those arc length calculations are, right? Like if I want to find the arc length of something, I'm doing that, adding up all the magnitudes of the ds's. And it looks like such a simple little function there. But for those of you who've done it, you know that it can be quite mathematically challenging. And in fact, often yields integrals that are not solvable analytically and have to be solved numerically. But I'll leave that for your calculus teachers to talk about. For us now, what we want to do is look at some more interesting forces and really test this notion of path independence. So what we're going to look at are actually two-dimensional forces that are functions of position. So f of x comma y. So the force is a function of both its x position and y position. And the first one we're going to look at here is negative x I hat minus j, minus y j hat. Okay, and so, well, what does that force look like? If you start plotting points like at 1, 0, 0, 1, and you say, well, if I draw the force vector of what would happen at those points, what would that look like? Well, what you find out very soon is that what you are getting here with the force of this form is something that's called a vector field. And I've used a really neat program here that allows us to plot simple vector fields. I put any function in here for f1 and f2, where f1 is our x component of the force and f2 is our y component of the force. and then plot that vector field. Okay, so what you notice here is that no matter where you are, what this is saying is a force is always going to be pushing you towards the origin, and it pushes you towards the origin with a force that actually grows the further and further you are from the origin. You can almost think of this like a hemispherical bowl, right? If you have a marble in a hemispherical bowl, right, when you move it a little bit to the side, a force arises that tries to push it to the bottom of that bowl. And as you go further up those curves, that force does increase. So that would be something that a physical system that might yield this force, right? But what we're going to do is we're going to show whether or not this force is conservative by, this is sort of a mess, but what we're going to do is we're going to pick 2 points in this space, and I'm going to pick the origin and maybe the point, 2, 4, right? So that's the point 2, 4. And what I want to do is show a couple of paths moving from the origin to 2, 4, and see if I get the same amount of work along those paths. And every time we do these are called path integrals, where we're integrating along a very specific path. So it's not just merely between 2 bounds, because it's weird. I have a multivariable function here. So the path that I choose to go between those bounds is really important. And we're actually going to look at 3 paths. And the first path, a nice simple path that we can take, is what happens, let me actually do this in red. What happens if, better red pen. What happens if I move out along the x-axis to x equals 2, and then up along the line x equals 2, all the way up to 4, right? And so that's going to be our path 1. That's path 1a and 1b, right? So that's going to be the first path that we'll use. So path 1a is along the line y equals 0 from x, goes from, there's an element above it. X goes from 0 to 2. And then path 1b is along the line x equals 2 from y equals 2 to, that should be equals, y equals 4, right? And that gets us there. A simpler path, path 2 here, is just the straight line connecting the 2 points, right? So the straight line connecting the 2 points, what is that? Well, that's along y equals, if you look at that slope is 2, so y equals 2x. Nice simple thing, right? So that's from 0, 0 to 2, 4. And now let's just test one additional path. And the last path that we're going to test is, well, why don't we have a nonlinear path in there? And I chose these points obviously fairly strategically because the parabola y equals x squared nicely goes between those points. So along y equals x squared, once again, from 0, 0 to 2, 4, right? And so that's how we do these path integrals. We pick a couple of paths between those. Now, some people might be saying, well, Mr. Vaughn, choosing 3 random paths between 2 points is not sufficient to show that if the work along those 3 paths is the same, that would be the same for any paths. And to you, I said, sure, right? This is not as rigorous as we could make it. We would try to do this with arbitrary functions, and I'll talk about another methodology that gets used if we're trying to do this really formally. But at this level, that level of rigor is really just not worthwhile, because I'm going to tell you, as long as you can do this piecewise path, the straight line path, and a curve path, for 99% of the functions out there, you're going to come up with your answer, right? And by the way, there's other methods of verification for this as well that could let us know, but this should be sufficiently analytically rigorous for the majority of cases. So what do I do here? Well, each of these things starts with, every time we're going to do this, we're going to start with our basic definition of work. Work is the integral of force dot ds, okay? And then what I'm going to do is I'm going to put in what I know. I know that this force is negative x I hat plus negative y j hat dotted with, and the ds vector. A ds vector is a little change along the path. Well, any ds vector, if we're going to put it in ijk notation, is going to be a little movement along x, I, plus a little movement along y, j, right? So step one, pick our paths. Step two, we're going to write out the force and the displacement vector in our ijk notation, and then we're going to evaluate this dot product. So I end up with, remember what the dot product does is it multiplies together like things and then adds together the parts that you end up with. So this ends up being negative x dx, and then it's going to be negative y dy. But remember, the integration operation distributes across addition, so I'm going to then just have this in its own integral. So now this is nice and clean. Why is this nice and clean? Because now this is integrable, right? We know that when we're setting bounds, the bounds here are going to be x points, and the bounds here are going to be y points. If I'd left that as one big integral, like what would the bounds be, right? But here, now I can evaluate just the x parts, just the y parts. Easy peasy. And so now what we're going to do is, now that we've established our general work equation for this particular vector field, we're going to evaluate our paths. So here we go, path one. So path one. And here's where we apply the path. So path work 1a specifically. Now remember what 1a said. That was along y is equal to 0 from x equals 0 to x equals 2. So if I'm looking at this integral here, so negative x dx, that's all fine. Oh, and I'm going from 0 to 2 along there. Great. And then plus negative. Now here's the thing. I'm saying I'm evaluating this integral in this vector field specifically along this line. No matter what I'm doing, as long as I'm moving along this line, there's no y component of the force, right? Which is why I'm able to just put in 0 there for the y. So this whole thing is going to zero out. And now it's actually going to zero out for another reason, because what's happening to, this is saying, the bounds say, what's happening to y along this path? Well, y is going from 0 to 0 as well. Either of those two reasons are reasons why I could just say, boom, this entire integral goes to 0. Delightful. And then I can just quickly do this. So this is negative x squared over 2, evaluated between 0 and 2. And then we always show our evaluation. So negative 2 squared over 2 minus a minus 0 squared over 2, right? By the way, the more advanced you get in calculus, the more likely this is the step where you make your error, because you try and do all the math in your head and don't show the work. Nope. Do the antiderivative. Plug it in. Notice it's not a 4 here. It's a 2 squared, right? Because it's a plug-in. And then we can go to some evaluation from there. So this is negative 2 joules, because we know that that's just going to go to 0. Fantastic. And so that's the work done along path 1a. So now let's do the work done along path 1b. So work 1b, let's remind ourselves of what that is. That is along x equals 2 from y is equal to 0 to y equals 4. I'm off the top. There we go. So here we go. So along x equals 2. Ooh, so I can actually plug in the 2 here for x, because I know that that's going to be what's true about the force throughout this entire path. But what are the bounds? Well, if I'm actually going along the line x equals 2, the bounds are from 2 to 2 as well. Okay, well, we see what that's going to do. We know that that term is just going to go away as well. So that's sort of nice. And so now here we go, negative y dy, and from 0 to 4, right? Pretty straightforward. So negative y squared over 2 between 0 and 4, negative 4 squared over 2 minus a minus 0 squared over 2, and this is just negative 8 joules. Therefore, the work done along path 1 is going to equal the work done along path 1a plus the work done along path 1b, or negative 2 joules minus 8 joules, or negative 10 joules. Great, you found that. Awesome. So now moving on. Let's find the work done along path 2. The work done along path 2, this is the line y equals 2x from 0, 0 to 2 comma 4. Well, that's sort of easy now because I have, I know the x is going to change from 0 to 2. And, excuse me, the y is going to change from 0 to 4. And I have everything nice and separated. So this is really kind of trivial. So negative x dx from 0 to 2 plus negative y dy from 0 to 4. And there we go. And you're thinking to yourself, well, man, the path doesn't matter because there's no substitutions I can really make. It doesn't matter. I can just like evaluate this. X squared over 2 from 0 to 2 plus a negative y squared over 2 between 0 and 4. And actually, I'm not going to redo that work because we did that in the last problem. I know when I do this evaluation, I get negative 2 joules. When I do this evaluation, I get negative 8 joules. So that kind of works. And at this point, you're probably thinking, oh man, this is easy. Like, why do we even need to know the path? Well, that's sort of like, why do we need to know the path? Apparently for this force, we don't, because I hope you kind of see that this force is going to end up being a conservative force, right? But if we were to do the next path, path 3, which is along the line y equals x squared from 0, 0 to 2, 4, and I start plotting it all out, and I realize very quickly, oh my God, this is going to be identical. I'm not going to redo the work. Why would I redo the work, right? Nothing about these two integrals change because of the path. So there we go. Now, I do want to bring up something that we could do here. Looking at this, because we have the path, there is something we could do with actually either of them. I'm just going to do it the y one just to show a point here. I could say, well, I know that y is equal to 2x. So let's look at this thing. If I make this 2x dy from 0 to 4, you may say to yourself, like, why did you just do that? You made your life terrible. Because now you're trying to evaluate an x, but the operations with respect to y, you can't do that. You have to do a transformation in order to get it. Well, luckily, I can just do y is equal to 2x, and then dy dx is equal to 2, and therefore dy is equal to 2x dx. So I could actually solve that. And if we know, if we go down here, I go negative 2x, and then the dy becomes 2 dx. But now, because this integral is in terms of x, I would have to actually change the bounds. And the bounds would now become from 0 to 2, because the bounds are always reflective of what it's with respect to. So looking at that, I get negative 4x dx from 0 to 2. And then when we evaluate that, that's negative 2x squared from 0 to 2. So negative 2 times 2 squared minus negative 2 times 0 squared. Okay, so that's still negative 8 joules. We get the same thing. Oh, so that's interesting. I was able to use the path there, but not very usefully because this was so simple. So we're just going to come to the conclusion then, because the work path 1 and the work path 2 and the work path 3 are equal, therefore the force, the field force, negative xi hat minus yj hat, is conservative. Okay? Now, once again, I said this is not the most rigorous way we could do this. We could do this by creating an arbitrary path between the 2 points. I don't even have to have them be, stated points. I could have them be like a comma b and then c comma d, and then write my equations for my path in terms of those as well, right? Like along the line y equals a from, from whatever it is to whatever it is, was A to C, and then along the line, X equals B from B to D, and then, then the straight line would be some sort of atrocity of Y equals X, and then you could the coefficient there would be the slope of those with those points, and then I could construct a curve between them. So I could do it generically. It doesn't really get all that much more interesting. All it does is just gets more algebra-y, and it doesn't really illuminate anything real. The real way you do this, if you want to be more formal about it, is it becomes a problem of induction. So you take an arbitrary curve between them, and then you tweak the curve a little bit, and then prove that the next case doesn't change the outcome. And then if you've done BC calculus and all those stuff in 444 you know that the problem of induction is a horror show, right? It is dreadful, but it is a way of more generalizing doing this. And that's another method of being more rigorous, but once again, not usefully more rigorous for what we're doing. So rigor for rigor's sake is just about rigor mortis, and we don't want that. So let's do another example. Okay. And so let's look at the following. I'm going to do two more examples. So let's say the force is of the form negative y I hat minus x j hat. So a little bit different than before. I kind of switched things. Hopefully you see now that when I do this, the path is going to come into play. So the first thing we want to do is get a flavor for what this looks like. Once again, I'm going to pop back over to my vector field plotter. And you can see that I have, I have plotted, nope, that's going to be the next one we're doing. Nope. Oh, I need to put some negative signs in front of those, right? Just so we can get that. There we go. And so that's the field force that we're looking at here. You'll notice it sort of generally pushes you in this direction in the first quadrant, in this direction in the second quadrant, that direction in the rather in the third quadrant, this direction in the second quadrant. So it sort of like pushes things sort of like in and out, right? That's what's going on there. I'm not sure exactly what might yield such a force. Oh, I know. Think of a saddle. Right? A saddle which has a slope part here and a slope part here. And so you slope in from here and then out from there, right? That might be what this looks like. That might yield a force of this construction. But let's go back and we're going to do our work here. And we're going to use the same three paths. So we're great paths, lovely paths. So we might as well use them again. So first, let's create our work function that we'll be using. So negative y I hat plus negative x j hat dot with dx I hat plus dy j hat. And then here we go. So what do I end up with? Negative y dx plus negative x dy. All right, that's what, dy. That's what we get. Oof, this is going to be a little bit more complicated because I've got y's on my x's and x's and y's. So I'm going to need to do some transformation work and really use the paths in this case, right? So the last one, I didn't really use the paths all that much, which then made sense why it was a conservative force because the path didn't matter. I wonder here where mathematically we're going to need to use the paths, whether that same result occurs. So here we go. Path 1A. Once again, what is path 1A? That's along the line y equals 0 from x equals 0 to x equals 2. So work 1A, here we go. Ooh, along the path y equals 0, that's going to be great. That's just going to solve that problem there because even though I'm going from x equals 0 to 2, that whole thing is just going to zero right out, nice and simple. And then here we go, negative x dy. Ooh, but because I'm moving along y equals 0, the bounds here are from 0 to 0 because there's no change in y. Perfect. Great. There you go. Apparently, moving along the path, moving along that line, there is 0 work done. And that is a delightful conclusion to that. And so if we look here, hopefully that'll make sense. If we're moving here, if we were to actually look at what's going on, we would find out if they plotted points that force would be acting perfectly straight downwards as I'm moving along the x-axis. And therefore, since the force is perpendicular to my displacement, it's no wonder then that I come out with a 0 work for that path. Cool. And so now we're going to do path 1B, and that's along x equals 2 from y equals 0 to y equals 4. Okay? And so work 1B equals. And so here we go along, so negative y dx. Oh, but I'm going from 2 to 2, so I don't have to worry about that. That first one is going to go from 0 because there's no change in x as I'm moving along this part of the path. Plus, and then I have negative x, but x is always 2 for this, which is great, dy, so from 0 to 4. So there is work done on this path. I'm going to end up with negative 2y evaluated between 0 and 4. So negative 2 times 4 minus a minus 2 times 0 is equal to negative 8 joules. Now, there's someone out there going like, why is he plugging in the lower bounds when we know it's going to go to 0? Because it's a really bad habit not to. Because when you have more complex functions, the lower bound doesn't always go to 0. And I just happened to pick a point where 0, 0. Maybe I probably should have picked the point 1, 1 so people wouldn't say, oh, I'm just going to not do it. Don't not do it. Don't fall into bad habits on easy problems because they will end up screwing you on harder problems. Develop good work habits when things are simple so you have tools in place for when things get hard. All right, sorry, a little screed there. All right, so next we're going to go along the path. So this is path 2, along the path y equals 2x. And then we're going to go from, just our points 0, 0 to 2, 4. And here we're going to really use the path, right? So work 2 is going to be equal to negative. Now we know it's negative. Just put the form out there, negative y dx. Oh, well, I can just substitute in 2x then for the y, right? And then dx, and that's going to go from an x value of 0 to 2, okay? Plus, and what I'm going to do next here is I go, okay, well, negative x. Well, there's 2 ways I can do this. I could either do the transformation, or I could just say, oh, well, if y equals 2x, then x equals y over 2. So y over 2 dy. I'm going to do it the other way with the transformation in just a second, so you can see we get the same answer. And that's going to be between 0 and 4, since we are evaluating this with respect to y. And so what do I get there? I get negative x squared between 0 and 2, right? I've lost my minus sign here. Minus, and this ends up being y squared over 4 from 0 to 4. So negative 2 squared minus a minus 0 squared, and then plus, really it's plus, because I like to think of that plus sign there. I like to think that as a coefficient. I just generally don't have as, I find that when people pull the negative sign out, they forget if this has a multiple terms in there to factor it back in appropriately. Once again, good habits, right? So I've got then negative 4 squared over 4. No, I just phased out there from minus 0 squared over 4. Okay, so what do I have here? I have minus 4. And then, that is also minus 4 or minus 8 joules. Oh, that's good, because that's what I got for path 1 holistically. This is great. I do want to show you that I could redo this second term, which was technically negative x dy by doing a transformation. So if y is equal to 2x, we showed before by taking the derivative that dy was equal to 2dx. And so if I do that here, I get negative x times 2dx, right? And now that I'm evaluating with respect to x, I'd go from 0 to 2. And so if I do that now, that's the integral of negative 2x dx, which is equal to between 0 and 2, which is when you evaluate that, negative x between 0 and 2, which we already know is negative 4. So I would end up with my negative 4 as well. Awesome. So either the transformation using the derivative or by manipulating the original function. All right, so let's do path 3. So path 3 is along the line y equals x squared between 0, 0 to 2, 4. Right, so here we go. So work 3, once again, using my template. I'm going to go from negative, well, this is x squared dx, great, and between 0 and 2, so just the direct substitution then, and then plus, and now I have some choices about what to do here. Either I could transform the function or I could take a derivative. Now, if you transform the function, what do you end up with? Well, if I transform the function, I would end up with having to take the square root of both sides. And here's the thing when you take the square root of both sides, plus or minus. So we have now put in some uncertainty into our problem. So I'm going to posit here that because the derivative always gives a unique answer, sometimes it's not worth transforming the path if the transformation of the path brings in things like domain restrictions that you don't intend that bring in, like for example, if my path was y is equal to e to the x, and then I undo it, now I have natural log of y is equal to x. Well, there's a domain restriction on natural log of y that we didn't have in the problem, and maybe the paths that were possible before are no longer possible. Same thing here as well. If you would pick paths with negative values of y, this becomes an impossibility. Therefore, it is better to do the derivative method if it's going to introduce anything like that. So knowing that, I'm going to do dy dx, because it's not that hard. It's just 2x. Therefore, dy is equal to 2x dx, right? But if like the function's simple enough, fine, just move everything around, right? But just be careful. So then I've got so negative x times dy, which is 2x dx. So that's between 0 and 2. Let's actually clean that up a bit. So I've got from 0 to 2 of negative x squared dx plus, and this is negative 2x squared dx. Why evaluate that function twice when you can really do it once? I'm just going to collapse these two together, because in the same way that the integral is distributable over addition, I can also like group and factor now. So this just ends up being from 0 to 2 of negative 3x squared dx. And that actually yields for a very nice result, because when I take the antiderivative, then I just get negative x cubed, right, from 0 to 2. And very clearly, negative 2 cubed minus 0 cubed is negative 8 joules. And once again, work 1 equals work 2 equals work 3. Therefore, conservative, right? So this weird field force is conservative, even though it was multivariable and it seemed like the path might matter, but it doesn't. So let's do one more. I wonder what's going to happen here. But here we go. So the third vector field that we're going to look at is this fun one here, the pinwheel. Okay, and so this is a force of form y is equal to yi hat minus xj hat. So it's very similar in structure to the last problem, right? Because we had minus yi hat minus xj hat, and now we just remove one of them, and let's see what result that has. So we're going to do the same sort of thing. So we're going to start with the work equation, f dot ds, vector, and so that is yi minus xj dotted with dxi plus dyj, and that gives us y dx plus a minus x dy. Okay, now the great thing here is that we're going to be able to steal quite a bit of the work that we did before because it's structurally very similar, because we're going to do the same paths. So work along path 1a. Once again, that's along the line x equals 0. So that's going to go from 0 to 0, y dx plus, and I know that it's along the line x equals 0, so that's going to go away. And even though, I'm sorry, we're going, I need to slow down here. I have this backwards because I'm trying to do this too quickly. It's along the line y equals 0 from x equals 0 to 2. So let's try that again. So along the line y equals 0, so that's the first one, 0 from 0 to 2, plus, and who cares here because the y bounds are from 0 to 0, of negative x dy. Okay, it's not enough to be right. You have to be right for the right reason, right? Okay, so 0. Okay, so that's similar from before. Looks like no big deal. So work done along path B. So now let's look at that. So y is dx, but now I know I'm going from an x of, so this is along x equals 2 from y is equal to 0 to 4. So once again, x is not changing, so it's going from 2 to 2. So that's going to go to 0 plus a negative x dy, but x is 2 everywhere here, so dy from 0 to 4. Okay, that's the same integral that we got before. This is going to come out to be negative 8 joules, so negative 8 joules. So seemingly no change there. So now let's move to the next path. So this is along the path y equals 2x. So work 2. So let's look at our template. And so y equals, so this is going to be 2x dx from x equals 0 to 2, and then plus, we might as well just do the swapping one because that's nice and simple. Here, we don't have to worry about any sort of weirdness. So negative y over 2 dy from 0 to 4. And if we let's look back, we can kind of steal some of our work. And normally you don't really steal work unless you've done the work yourself. And generally you're not doing like 3 or 4 of these in a row, but never mind, I can't seem to find the piece of paper, so we'll just evaluate it. X squared from 0 to 2, and this is going to be negative y squared over 4 between 0 and this is 4, excuse me. And so now I have 2 squared minus 0 squared, and then plus a negative 4 squared over 4, minus a minus 0 squared over 4. All right, so that's 4, and then this comes out to be negative 4. Oh, interesting, no work is done along this path. So right away, we can see that the work done along path 1 is not equal to the work done along path 2. This is not going to be a conservative force. But for sake of completeness, we're going to finish the problem. So along the line y equals x squared, and from having done the work before, we know that dy is equal to 2 dx, right? Because we've shown that work before. So work 3, we're going to put in our template here, x squared from 0 to 2 with respect to x, right? Plus, and then this is going to be negative x, and then 2 dx with respect, and then this goes from 0 to 2 now because I've changed the bounds as well. And I'm going to get x squared, or x cubed over 3 from 0 to 2. And then this ends up being, this is 2x. Once again, got to be careful. Don't want to go too quickly. So I'm evaluating negative 2x squared, right? So that becomes negative 2x cubed over 3 between 0 and 2. There we go. So looking at that, what do I have? I got 2 cubed over 3 minus 0 cubed over 3. And then plus a negative 2 times 2 cubed over 3 minus a minus 2, 0 cubed over 3. What we have there? We have 8/3 is that one. That goes to 0, that goes to 0, minus 16/3 or negative 8/3 joules. And once again, I'm getting that work 1 is not equal to work 2, is not equal to work 3, and therefore this force is non-conservative. Okay, so why do the third path? Because in these problems, when the function gets funky, you sometimes make mistakes, or it could be happenstance of numbers that the two paths, you could have messed something up with the two paths and therefore get the two different results. It's best just to do the third one, see if you get yet another different results, just so that you can double check yourself. So there you go. That's how you do this. So what I want you to do is try this one. So let's say our force is equal to negative y squared I hat minus 2yx j hat. So that's the function that I want you to ask, is it conservative or not? I want you to use the same 3 paths that I used between the same 2 points, right? So let's just look to see what that looks like when I plot it in here. So 2y squared, okay? And then this is minus 2xy. Let me put that in. And this is freaky looking, right? Oh, let me actually zoom out a bit. Yeah, I don't know what to tell you. That's what that looks like. It doesn't seem to do that much around the origin, but then as you go away from the origin, especially in the first and fourth quadrants, man, that's getting you places. So I want you to see if you can prove if this is a conservative force.